All right, I just want to do a couple more examples of the integral test first, and then there's one other thing to talk about in this section. All right, so let's look at this one. The infinite series n equals 1 to infinity of 1 over n squared plus 1 all in the denominator. All right, so the question for this is just going to be, does this converge or diverge? Whenever that question is asked, you have your list of tests that you have available to you. Right now, we've only talked about two. We've talked about the nth term test, and we've talked about the integral test. Nth term test is always what you want to start with, so let's talk about that. With the nth term test, remember you want to look at the sequence values, which is just the 1 over n squared plus 1, and then take n to go to infinity. Well, if we take n to go to infinity of the sequence terms, the denominator would blow up to infinity, and we would get 0. Remember, with the nth term test, if the limit of the sequence goes to 0, that means the test is inconclusive. All right, which means the only other option that we have is to try the integral test. Remember, with the integral test, you have to satisfy those prerequisites. You have to have that your function is always positive, which it will be for n equals 1 to infinity, always decreasing, which it also is from 1 to infinity, and there was other thing. Oh, continuous. So this is continuous from 1 to infinity as well. Sometimes you're going to have functions that don't just start off decreasing right away, and note that that's okay. It's okay if it doesn't decrease immediately, it's just as long as it decreases eventually. Then what you're going to do is you're going to integrate over the same sequence but as a function. So 1 over x squared plus 1 dx from 1 to infinity. All right, this is listed on that table of integrals. The antiderivative is tangent inverse of x. And then this we're going to evaluate from 1 to infinity. I think I've talked about this before. I don't really remember with you guys. But tangent inverse, you can just look at the graph for what that does and think about the horizontal asymptotes for it. The tangent inverse graph goes to pi over 2 as your x goes to infinity. That's going to be minus plugging 1 into this, and tangent inverse of 1 is pi over 4. Pi over 2 minus pi over 4, pi over 4. Okay, so we did the integral, and the integral converged to pi over 4. That means what we can say is, since the integral converges, we also get the series converges by the integral test. Just because the integral converges to pi over 4 does not mean that the series converges to pi over 4. We have no idea what this converges to. All we know is that it converges. All right, one more quick example of this. Let's look at the infinite series. Let's go n equals 1 to infinity of n e to the negative n squared. Same thing, you'd want to try the nth term test first. We'll just go ahead and nix that. Just know that the nth term test is going to be inconclusive. This does go to 0. Next thing we would try would be the integral test. With the integral test, we would do the integral. So here's where we have to be a little bit careful, because I don't know necessarily if this is decreasing right away or if it takes a little bit. So what I would do is I'd probably go into Desmos and I would just graph it. So we are looking at the graph x e to the negative x squared. All right, so 1 is here. Remember, we're starting at 1 and it is decreasing forever, so we're fine. Let's just pretend that maybe it was increasing to 3, and then at 3 it started to decrease. That's okay as long as you make your integral to be from 3 to infinity. But for us, since we decrease from 1 to infinity, we'll just leave it there. And then we're going to be integrating over x e to the negative x squared dx. All right, we can do the antiderivative for this pretty easily. Just do a u substitution. Let u be the negative x squared. Du then would be negative 2x dx, which means that when we do the substitution, it's going to be the integral over 1/2 e to the u du. That has antiderivative 1/2 e to the u. And then we're going to plug back in the u. So here we're going to have 1/2 e to the negative x squared. That evaluated from 1 to infinity. All right, so just be a little bit careful when plugging in infinity into this. This e to the negative x squared is really going to be in the denominator because of the negative sign. It's going to blow up to infinity, and since the denominator blows up to infinity, that first term is going to go to 0, and that's going to be minus plugging 1 into that, which is going to be 1 over 2e. So we get negative 1 over 2e, pretty awful looking number, but honestly it doesn't matter. The point is that the integral converged to something, thus the series converges. Okay, so that's the integral test in a nutshell. If the integral blew up to infinity or negative infinity, then that also means that the series itself diverges. There is one other topic I want to talk about in the section, so we'll go through it real quick, and that's something called error estimation. What we can do with this integral test is that we can actually determine kind of a range of values that our sum may be located at. I have this whole big thing kind of written up in my notes here. I would recommend looking through these calculations in the book. I'll just kind of get to the final result. The final result is this. The integral from n plus 1 to infinity over f of x dx, that is less than or equal to this remainder term. Let me see. I'm going to rewrite this a little bit. Sorry. If you're already writing this stuff, it's okay. I'm just going to add something to the front of it. I'm going to add the partial sum. The partial sum plus this integral is going to be less than or equal to the actual sum is less than or equal to the partial sum plus the integral from just n to infinity. All right, so I know I'm just throwing this out of nowhere, but I promise you there are some really neat and clever calculations that go into it. Just know that this is going to be true. If you want to find bounds for the actual sum, you're going to take the partial sum plus this integral and bound it below, and then the partial sum plus this integral to bound it from above. So we'll just do a quick example. Estimate the infinite sum going from n equals 1 to infinity of 1 over n squared. Okay. Cool. So we know this converges. This converges because it's a p series and my p is bigger than 1. We just have no idea what it converges to. To find what it converges to, we could use this little inequality here. Let's just use n equals 10. If this was a quiz or a test question or even a homework question, it would just give you the number to start with. So we're starting there. First thing we would need is we would need to know what the partial sum is of the first 10 terms. So that's plugging in 1 through, I guess it would be 1 through 11. We'll just go to 10. We'll just go 1 through 10 here. So it's going to be 1 over 1 plus 1 over 2 squared, which is 1/4, plus 1 over 3 squared, so 1/9, plus 1/16, plus 1/25, and that's going to go all the way down to 1 over 100. Oops, not 110, 100. So I added these up already in my notes here. These add up to be 1.54977. Okay, great. The other thing that we would need is we would need to know what those integrals are. So let's just do the first one. This is going to be the integral from n plus 1 to infinity. If my n is 10, this is going from 11 to infinity of the function 1 over x squared dx. All right, so that we can find the antiderivative for real quick. The antiderivative is negative 1 over x. Then we're going to evaluate this at infinity minus evaluating that at 11. If I plug infinity into this, I'm just going to get 0 minus a negative, so plus, and if I plug 11 into that, I get 1 over 11. So this integral converges to 1 over 11. Then I'd also want to do the integral on the right-hand side of the inequality, which is just going from n to infinity. So for us, 10 to infinity of 1 over x squared dx. This is going to have the same antiderivative. Oh, geez, I keep hitting that wrong button, sorry. So this has the same antiderivative, so we're just plugging infinity in, which is going to give us 0, minus the negative of plugging 10 in, which is going to give us 1/10. Okay, Then if we plug all of that into this inequality, so it's going to be the partial sum of the first 10 terms, 1.54977 from here, plus the integral from 11 to infinity, which is 1 over 11. That's going to be less than or equal to whatever the actual sum is, which we don't know. And then that 1.54977 plus 1/10. All right, I went ahead and found these for us. That's going to be 1.64068 is less than or equal to the actual sum is less than or equal to 1.64977, I think. Okay, cool. So again, what this inequality allows us to do is it allows us to approximate the sum. And notice that we're already pretty decent, right? We're within a hundredths of a decimal here, or 4/100ths of a decimal. Okay, but that is section 3.